Hello students, today we'll start chapter 3C, linear momentum and Newton's second law of motion. And in that we'll start with linear momentum. Linear momentum of a body is the product of mass and velocity. In simple terms, it is the product of mass and velocity. That means mass denoted as m, velocity denoted as v, hence it is written as m into v. It is a vector quantity and its SI unit is kg meter per second. CGS we can write gram centimeter per second. In our common experience, that if two bodies of different masses are moving with the same velocity, they are brought in rest in the same time. The force needed to stop the heavier body is more than that of the lighter body. Similarly, if two bodies of same mass are moving with the different velocities, then to stop them in the same time, the force needed for the faster moving body is more than for the slower moving body. Thus, the force needed to stop a moving body in a definite time depends upon both mass of the body and its velocity, which gives us linear momentum, which is the product of mass and velocity. Now, to calculate the change in momentum, we denote it with this symbol, that is read as del, written as a small triangle and is read as del. Del means a small change in momentum. So here again on the opposite next side, right hand side also we have a del mv. Sometimes their mass is constant, so we have always change in velocity, and in few cases where velocity is constant, in case of atomic particles moving with velocity comparable to the velocity of light, mass is variable, then we write del mv. Del means a small change in the momentum. Now next is rate of change of momentum. Rate of change of momentum means change of momentum divided by time. Simple terms. Rate of change of momentum means momentum divided by time. Momentum is mv. So mv, rate of change of momentum is written as here m. Instead of v, it is final velocity minus initial velocity by time t. Now Newton's second law says that force is directly proportional to the product of rate of change of momentum. This was the statement. So F is proportional to m v minus u by t. This sign is the sign of proportionality. So when this proportionality is removed, we have a constant. Here constant is k, so which is equal to m v minus u by t. So instead of v minus u by t, it is velocity by time, that means acceleration. So force is equal to kma. So when we have a is equal to 1, m is equal to 1, we write that 1 Newton is equal to k1 g, and velocity per unit time is 1. That means k is equal to 1, and hence we get our equation that force is equal to mass into acceleration, which represents the Newton's second law. It states that force is equal to mass into acceleration. According to the statement, the rate of change of momentum of a body is directly proportional to the force applied and takes place in the direction in which the force acts. That means the rate of change of momentum of a body mv by t is directly proportional to the force applied. Now we'll discuss few examples related to this relation. Rate of change of momentum means force is inversely proportional to the time taken. From here you can see it is directly proportional to change in momentum and inversely proportional to time taken. So Newton's second law, all the examples and applications are based on this formula only, that is force is inversely proportional to time taken. A very simple and very easy example is that while catching a ball in cricket, the cricketer withdraws his hand along with the ball. So we pull our hand back to get less hurt. That means when we are pulling it back, the time period increases So now let's see how the calculation is done for this example. Suppose our initial velocity is u, final velocity v, so it is 0 because it stops in our hand. Initial momentum will be m into u because initial velocity is u. Final momentum will be 0 because v is 0. So change in momentum 0 minus mu, and which can be written as minus mu. Here negative sign shows that the change in momentum is in the direction opposite to the initial direction of the motion. Now if the cricketer does not pull his hand back, that time, let's suppose our time period is t1, so force will be mu by t1. Now when the cricketer pulls back his hand along with the ball, so time period is t2 and the force will be mu by t2. Now we know that t2 is greater than t1 because he is taking a lot of time to pull his hand back. Therefore the force F2 will be less than force F1 because T2 is inversely proportional to F2. So where time period is more, force will be less. Here in case of T1, time period is less, but it is inversely proportional, so force will be more. So force exerted in the case of F1 it will be more than that in the case of F2. So a cricketer pulls his hand back to get less hurt. Now one more example is that when athletes often land on sand or foam after taking a high jump. When an athlete lands on a hard floor, he may hurt his feet because his feet or his back comes to rest almost instantaneously. So a very large force is exerted by the floor on his feet. On the other hand, when he land on sand or foam, his feet pushes the sand for some distance, therefore the time duration in which his feet comes to rest increases. So time increases, that means the force exerted will be less. As a result, the force exerted on his feet decreases and he is saved from getting hurt. So these two examples, one more is that when a glass vessel fall on a hard floor, they break, but they do not break when they fall on a carpet. So in that case also what happened? Time period increases. So in Newton's second law, all the examples are based on this relation only, that is force is inversely proportional to time period. So wherever time period will be more, force exerted will be less. So practice these examples. Few more topics left on this topic we'll discuss in next video along with the numericals. Thank you, students.